when speed of a fluid increases, pressure decreases. Correct? Let us now derive the equation required for it. It's a very simple, straightforward equation. Now, before we do this equation, we need another equation which is equally important. In fact, probably even more important. So, suppose I had like a tube that went that way. Now, the area of cross section of this tube changes, right? So, let us say the area was A1 here, and the area of cross section is A2 here, and the area of cross section is A3 here, and suppose I say that this was A4. Okay. Now, I am going to claim that this is a liquid, incompressible liquid. Now, this is not true for gases. It's only true for incompressible fluids. Okay. Now, we are also going to claim that this fluid was basically everywhere here, all the way like that. That means it fills the entire tube, and it fills the entire tube here. But at this part it does not fill the entire tube. Let us say that it goes till there. It's possible, right? Suppose suddenly it opens up, it won't necessarily fill the entire part. And this fluid is entering this way, going out like that, and continuing to go flow further down. Okay. Now, generally people stop from here to there. I am just extending it so you know when it works and when it does not work. Now, if you look at this fluid, the total mass of the fluid contained here will be the same. Basically, it depends on the volume into the density of the fluid. New fluid comes in, new liquid comes in, but then corresponding amount of liquid must get out. Correct, because you can't increase this. What if you increased it? That means the density has increased, but I just told you it's an incompressible fluid. There is no place for it to expand into. So, given that it cannot increase in volume and it has constant density, what does it mean? The amount of fluid or the mass of the fluid must remain constant. Any new fluid that comes in must get out, or an equivalent amount must get out. At the instant this guy comes in, obviously this guy isn't getting out, but something else of the same size must get out. Same volume must get out because it's incompressible. Mass gets out is equivalent to volume gets out because the density remains constant. Now, if I look at how much comes in, where is it coming in from? From this side. In 1 second, let us say the liquid here has velocity v1. Okay, in 1 second, will these molecules enter? Maybe. Will these molecules enter? Maybe. Will these molecules enter? Maybe, maybe not. How do you know till when the molecules will enter? Okay, everything that was up to a distance of v1 will enter within 1 second, because the molecule here takes exactly 1 second to reach there. Why? Because its speed is v1. This molecule will take less than 1 second. This will take even lesser time. This will take a small fraction of a second and then it's gone. So, but all of these guys would have entered in within 1 second. By the way, this is a very important and useful idea, because this idea we will later look at for current, flow of current, look at for flow of electrons. We will use this again and again. What is the idea? I am taking velocity and converting it into length for 1 second. But velocity is length for 1 second. So, everything here would have gone inside. Anything here would have just reached this part but not yet gone inside. So, how much enters in 1 second? This much enters in 1 second. But how much is this much? It is A1 V1 into rho, but rho is anyway constant. So the volume that enters in 1 second, enters this border in 1 second is A1 V1. But if that much enters in, that much must get out. But you look at this cross section, it is smaller, A2. Now this part, it has velocity V2, and a lot more has to, well, this much is the amount that will get out. Now all this is not the getting out. Actually, if you look at this portion, all these fellows who were V2 before would have got out. So not that, they would have got out to this part, but I am just trying to say that it is not because it is this V2. Finally when they come out, that's where they will be. But who are the ones who get out? They are these ones. So I am going to, let me make this a little longer so that it is easier to just follow. Because you can, instead of 1 second, make it a fraction of a second. You can make this smaller. But this volume and that volume must be equal. So up to V2 length, everything must get out. Well, these fellows will not be able to get, they may probably come to this part, but they wouldn't have crossed that boundary. So what is the volume here? A2 V2. And so we write A1 V1 must be A2 V2, because the volume of the water or volume of the liquid that came in 1 second must be the same as the volume of the liquid that gets out in that same 1 second. Is it the same liquid that comes in and the same liquid that gets out? No, because if, like, suppose I colored this with some blue color or orange color or something, that comes in here, and let's say that the color doesn't start diffusing. Maybe something which was not colored has actually moved out. This will reach there, but it will take some more time. But at the instant it is entering, at the same instant there must be a corresponding amount that must get out. This is like Kirchhoff's current law. All the current that comes in must get out. Right now whatever is entering must get out. Doesn't mean that it has to enter now and the same thing has to get out. Corresponding amount has to get out. Okay, it is the same idea. So we call this the continuity equation. Now is that also true for this guy? Yeah, because this thing is completely filled, right? So this one, the amount that goes out is A3 V3. So we can write this as A3 V3 as well. Can I say that about A4 V4? Why? Because now suppose this one I blocked, velocity is 0. Is there a problem? No problem, because as the water would come in, it will start to rise up there. So that means you can't conclude that this is A4 V4. You can't say that. So when can you say it? When the area of the cross section does not increase. But what if I had an open canal? What if I had something which was like that, and then this thing basically became little smaller? So you mean I can't apply it to something like this? In principle, yes, you can't apply. Okay, but if I want to apply, I want some general condition. Yes, this is one is, of course, if it's completely filled, then clearly A1 V1 must be equal to A2 V2, must be equal to A3 V3, but here it is not fully filled, so in which case it doesn't apply here. Okay, but suppose I told you no, it does not rise above this. In fact, it is filled till here and it does not rise. Then it will be equal to this area A4 dash times V4. And it will be equal because all you really wanted was that the volume that is getting out must be equal to the volume that is getting in, and nothing should basically start accumulating. So if I know for sure that liquid is not accumulating at a particular cross section, whatever comes in is getting out, then this statement is true. But in places where I am not very sure whether it's accumulating or not, but there is no place to accumulate, then you can anyway write this. Okay. But in other situations where the flow is what we call steady. What does steady flow mean? It's just continuously going and going in like this, going out like that, and so on. But if it starts to rise, the flow is not steady, because someplace something else is accumulating. Okay, so if you have a steady flow, then you can be sure that this is equal to this everywhere. For steady flows, that is not a steady flow. So continuity equation is true for steady flow of liquid. Okay. Now when we did this, we did use that it is incompressible. So it's only true for incompressible fluids. Is it true for gases? Well, for steady flow, the density is also not increasing. If you assume it's steady flow, density is not increasing anywhere. Even if it was compressible, you can technically use it because it behaves like it is incompressible. Okay. So as long as the basic idea is clear, what comes in gets out, and what comes in and what gets out are related by A1 V1 and A2 V2. No height increases like that, and steady flow. Okay. So those are the two main conditions under which this statement is true. Now this is true for very general situations. Okay. So therefore, does it matter that this thing was here? This should be pointing upwards, horizontal. Actually, all that doesn't matter. In fact, this could be turned around like that. It will still be true. Okay. Everybody is clear about this? Okay.